Have you ever been handed a math problem and just grabbed the numbers and started crunching away with some simple arithmetic? Yeah, we've all been there. But blindly applying arithmetic is incredibly risky, both in math and in science. Welcome to This Explainer. Today, we're diving into a mathematical wonderland to look at numbers that simply do not average well. Let's get right into it. So we'll start off with what looks like a ridiculously simple question. Imagine two algebra classes take the exact same test. Class A gets an average score of 80, Class D averages a 70. Now, if you want the combined average of both classes, you might just add 80 and 70, divide by 2, and boom, you get 75, right? Does the math just perfectly meet in the middle here? Well, actually, no, not necessarily. Your gut instinct might say yes, but it can be completely wrong. And here's the absolute core of why. Numbers do not just carry meaning all by themselves. They get their true meaning from their specific definitions and the real-world context they exist in. You can't just run an operation like averaging unless it actually fits the context of what you're looking at. Which brings us to Section 1, down the rabbit hole into hidden denominators. Let's look at exactly why our basic math just failed us on those test scores. The big issue here is that we're missing the hidden denominators, meaning the actual number of students in each class. Think about it. An average is already a summary of a group. Before we go and average two summaries together, we literally have to know what they summarize. What if Class A is packed with 30 students, but Class B only has 10? If you actually calculate that out, the combined average is 77.5. It's not 75. We totally ignored the true sizes or the weights of the groups. And that's exactly where this formula comes in. To combine group averages the right way, you have to use a weighted average that respects how big each group actually is. You basically multiply each group's average by its size, add those up, and divide by the total number of students. You can only average two averages directly if the groups are the exact same size. Otherwise, the simple math just falls apart.
Okay, moving on to Section 2, potions and the pH trap.
Let's step a little deeper into this wonderland with a chemistry puzzle. Let's say we've got two equal volume bottles of water. One is at a pH 4, the other is at a pH of 6. If we mix them together and apply our super simple arithmetic, does it just create a perfect pH 5 mixture? Again, the answer is a resounding no. But why? Well, it's because the pH scale isn't an ordinary linear scale like a ruler. It's actually a logarithmic expression of hydrogen ion concentration. And because it's logarithmic, you absolutely cannot just average those numbers together. They aren't behaving the way our brains want them to. To get the real answer, we have to ditch the simple average and follow 3 specific steps. First up, we convert the pH value back into the actual physical hydrogen ion concentration. Second, since we are mixing equal volumes here, we can safely average those physical concentrations. And finally, step 3, we take that new physical concentration and convert it back into a final pH value. Now, when you actually do that math, the final mixed pH is about 4.30. I mean, wow, right? That is shockingly far away from our gut instinct guess of 5. The mixture is way more acidic than you'd ever expect if you were just eyeballing a 4 and a 6. And the secret behind this wild outcome? Exponential math. See, a change of just one single pH unit is actually a factor of 10 change in hydrogen ions, which means pH 4 actually has 100 times the hydrogen ion concentration of pH 6. Because pH 4 is so overwhelmingly concentrated, it just dominates the mixture and pulls everything heavily toward itself.
That brings us to Section 3, through the logarithm glass.
So that pH example, that was basically a logarithm trick in disguise. Let's look at some standard base 10 logarithms. Let's say the log of A is 2, meaning A is 100. And the log of B is 4, so B is 10,000. If we average those logs, the 2 and the 4, we get 3. But what does that 3 actually represent in the real world? Here's where it gets completely wild. The standard arithmetic average of our starting numbers, 110,000, is 5,050. But that log average of 3, that actually corresponds to exactly 1,000. And 1,000 is clearly nowhere near the arithmetic average of those two numbers. This happens because when you average logarithms, you're actually finding what's called the geometric mean. The number 1,000 is the halfway point on a multiplicative scale, not a linear one. Think of it this way. Every step multiplies by 10. Going from 100 to 1,000 is one step of times 10, and going from 1,000 to 10,000 is another step of times 10. You're finding the multiplicative middle, not the additive one.
Section 4, Illusions of Everyday Math.
Now, you might be thinking, okay, that's just chemistry or advanced math, but these deceptive numbers are hiding in plain sight in our everyday lives. Take driving, for example. Say you drive 60 miles at 30 miles per hour, and then another 60 miles at 60 miles per hour. You cannot just average 30 and 60 to say you averaged 45 miles per hour. Speed is a rate. You have to go back to the underlying truth, the total distance, which is 120 miles, and the total time, which is 3 hours. Divide those, and your true average speed is 40 miles per hour. The exact same rule applies to percentages. You literally can't average 2 passing rates without knowing the actual population base of students at each school. On top of that, we have numbers that are really just labels acting in disguise. Think about room numbers. If you take the mean of room 101 and room 201, you get 151. Arithmetically, sure, that's correct. Mathematically, it is completely meaningless nonsense. Room 151 has zero logical connection to those two rooms. The same thing goes for zip codes, the jersey numbers on athletes, or your phone number. Just because it looks like a number doesn't mean you should be doing calculations with it. Which leads us to our final section. Section 5, Math is sense-making. So what's the big takeaway? How do we protect ourselves from blindly crunching numbers that just don't average well? Well, before you do any math, before you even think about reaching for a calculator, you have to ask 2 critical questions. What does this number mean, and what would the average actually mean? Are you dealing with original measurements, or are they already summaries? Are they rates? Are they on a log scale? Look at this quote because it perfectly captures what we've been talking about in this explainer today. Mathematics is not just about doing operations. It is about choosing operations that fit the meaning of the situation. Formulas are great, they're incredibly useful, but only if you use them according to their proper context. Because at the end of the day, true math is all about sense-making. I'll leave you with this final thought to ponder. The next time you're handed a shiny set of numbers, are you going to calculate blindly, or are you going to stop to uncover their true meaning? Think before you average. Thanks for joining me on this dive into the mathematics of context, and I really hope this helps you navigate the numbers in your own life a little more carefully.